Hello and welcome once again on the lecture series of course Elements of Machine Design. Myself Mr. S.S. Mali, Head of the Department, Sharda Institute of Technology, Polytechnic, Etro. Now we are in the lecture number 6. Up to this lecture we have seen the introduction to the syllabus, what is meant by the machine design, types of the machine design, what is the necessity of the studying this syllabus or this subject for the diploma engineers, what is considerations of the machine design, what is the design procedure of a simple element, how to design a simple element. We have also studied what is meant by the stress, what is meant by the strain. We have seen the different types of the stresses that are induced in the component. We have also undergone through these different types of the strains. So now we are in the lecture number 6. Today we will study the stress strain diagram. So you are actually studied this stress strain diagram in strength of the material also. So today we will just look different salient points of this diagram. Before going to the diagram, it is necessary to know what is the necessity of studying this stress strain diagram and how this diagram is formulated. We know that in designing of various parts of a machine, it is necessary to know how the material will function when it is subjected to the service. For this, we have to study some certain characteristics or properties of the material. That means we should know the different characteristics or properties of the material. The mechanical properties mostly used in mechanical engineering practice are commonly determined by conducting a simple tensile test. And by conducting this simple tensile test, we are actually formulating the stress strain diagram. Now, what is this simple tensile test? Now, this simple tensile test consists of gradually loading of a standard specimen of a material and noting down the corresponding values of load and elongation until the specimen fractures. Actually, you have conducted this test in strength of material practical on universal testing machine, that you have hanged a specimen of a mild steel, and in that procedure your goes on increasing or your goes on applying the load on the standard specimen until that specimen breaks. So during this loading, we are noting the load applied on the specimen and corresponding elongation. So the load is applied and measured by a testing machine. The stress is determined by dividing the load values by the original cross-section area of that specimen. In this way, the stress value is determined in a simple tensile test by using a universal testing machine. The elongation is measured by determining the amounts that two reference points on the specimen are moved apart by the action of the machine. Actually, this is the practical procedure. Actually, you have conducted this test, you have undergone this procedure, and you have determined the strain in that component. That means we are marking the 2 points and we are measuring the distance between that 2 points when we are applying the load on that component. The original distance between these 2 reference points is known as the gauge length. We know that before actually starting the test, that is the simple tensile test, we are marking that 2 points on that ductile specimen, that ductile bar, MS bar, that is the mild steel bar, and we are goes on increasing the load on that bar, and the first marking points are known as the gauge length. The strain is determined by dividing the elongation values by the gauge length. The gauge length is the reference length before applying the load, and when we goes on applying load, as we have studied in tensile strain, that elongation will take place in that mild steel bar as we are applying the tensile loading, because we are conducting the tensile test. The values of the stress and corresponding strain are used to draw the stress strain diagram of the material under testing. This is the basic how the stress strain diagram is drawn. Try to understand. The stress strain diagram is drawn by conducting a tensile test, a simple tensile test on a mild steel bar on a universal testing machine. When we apply the load on that bar, we are measuring, noting down that load, and we are measuring corresponding change in length. Then stress is found by using the formula corresponding load divided by cross-sectional area, and stress is found by dividing change in length to the original length of the specimen. In this way, this stress and strain is determined by using simple tensile test, and these values of stress and strain are plotted. Now, these are the corresponding values. These values are plotted by using these values, stress and strain value. Suppose this is the stress, this is the strain, stress, strain, stress, strain, and we get 2 points. This is stress, this is strain. Now this intersection, we are just drawing this intersection, we are getting these points, and we are drawing this stress strain diagram. Now understand, when we draw this diagram, after drawing this diagram by taking the values of stress and strain, we are getting the nature of graph as shown in diagram. This is the nature of graph that we get when we draw this diagram by calculating the stress and strain. Notice the values of stress and corresponding strain are used to draw the stress strain diagram of the material which is tested. Now, as shown in diagram, this is the stress strain diagram for a mild steel under tensile test. The various properties, or we can say silent points of the material, are shown on this diagram. Just go through this point. Now first, take this point O as the reference point, O as the reference point, O to A. Now as shown in diagram, up to point A we get a straight line, that is O to A. Means when we plot stress and strain values up to point A, we get a linear progression from the point O to A. Now this is known as the proportional limit. This is the proportional limit. From point O to point A is the proportional limit. Now we see from the diagram that from point O to A is a straight line which represents that the stress is proportional to strain. Now look at this, O to A, the stress is proportional to strain, means as we goes on increasing load, there is a corresponding elongation, means as the value of stress increases, the value of strain also increases. We know that stress is load upon cross-sectional area, and strain is change in length to the original length. Now up to point O, it is a proportional, means stress is proportional to strain, means as we go on increasing, there is an increase in stress, there is a corresponding increase in the strain. So up to point A we get a straight line. Now beyond point A, the curve slightly deviates from the straight line. It is obvious that the Hooke's law holds good up to point A, and it is known as the proportional limit. We know that Hooke's law. The Hooke's law is within elastic limit. Means when that material is within elastic limit, the stress is proportional to the strain. That is up to point A. That's why it is known as the proportional limit. And it is defined as the stress at which the stress strain curve begins to deviate from the straight line. Now from point A, the curve deviates. The curve is not straight line. From point up to point A, the curve is straight line, but from point A, the curve deviates. From point A, the curve deviates. So up to point A, O to A is the proportional limit. That means stress is directly proportional to strain. Now A to B is the elastic limit. Now till B, point B, the material is in elastic stage. Means when we remove the load from the material will regain its original shape. That is known as the elasticity of the material. Means up to point A, up to point B, the material is in elastic limit. But up to point A, it follows proportional limit. Stress means Hooke's law. From point A to B, though it is in elastic limit, but it does not follow the Hooke's law. Now A to B is known as the elastic limit. Now it may be noted that even if the load is increased beyond point A up to the point B, the material will regain its shape and size when the load is removed. This means that the material has elastic properties up to the point B. Now this point is called as the elastic limit. Now this point is known as the elastic limit. Now it is defined as the stress developed in the material without any permanent deformation. Without any permanent deformation. Means up to point B, if we remove the load, the material will regain its original size and shape. That is known as the permanent deformation. So up to point B, the material is in elastic limit. So point A to B is the elastic limit. Now from point B onwards, the curve slightly deviates. Up to point A, it is straight line. It deviates from A to B. Again, it deviates from B to C. There is increment in stress, but there is no large increment in strain. Small increment in strain. There is increment in stress, but there is no large increment in strain. If the material is stressed beyond point B, from point B, if the material is stressed, the plastic stage will reach. From up to point B, the material will be in elastic stage, but from point B, the plastic stage will reach. That is, on removal of the load, the material will not be able to recover its original size and shape. Now, beyond point B, the strain increases. Beyond, just concentrate on point B. Beyond point B, the strain increases at a faster rate with any increase in stress, until the point C is reached. Now at point C, the material yields before the load. It starts yielding. From point C, the material starts yielding. That's why it is known as the upper yield point. Point number C is known as the upper yield point. It starts to change its shape. Now up to point B, the material is in elastic state. But From point B, it loses its elasticity and it enters into the plastic stage. Now at this point, at the point number C, the material yields before the load and there is an appreciable strain without any increase in stress. Now at point C, there is an increase in strain but without increase in stress. In case of mild steel, it will seem that a small load drops to D immediately after yielding commences. Hence, there are two yield points C and D. The points C and D are called upper and lower yield points. The stress corresponding to yield point is known as the yield point stress. Now this is the yield point stress. And for ductile material, yield point stress is the design criteria. For ductile material, yield point stress is the design criteria. Now from the diagram you will see that the strain, even though strain increases, there is a decrement in stress. There is a decrement in stress. Why there is a decrement in stress? Because at this point the material has reached in the plastic stage. It is the phenomenon of grain formation, what we can say. The molecules or the particles of the material, if it holds good in the vicinity or they are in the close vicinity, then it will resist more. Yes, there will be more stress. If the particles of the material will go away from each other, that means there is a loose resistance offered by the or low resistance offered by the material. So there is a no stress. As we have already defined that stress is the actually resistance offered by the material to the applied load. So if due to the application of load there is an elongation of the material and these particles move away from each other and there is a slight resistance from the particles, hence there is a decrement in the stress value. Look at this, there is a decrement in the stress value at point D. This is known as the lower yield point. Now at point D, the specimen regains some strength. At point D, the specimen regains again some strength and higher values of stresses are required for higher stress. Now look at D to E. It is D to E and E is the ultimate stress. Now this is the highest value of stress. Means this is the highest resistance offered by the material. Actually stress is nothing but the resistance offered by the material to its breaking. So point E shows the ultimate value of stress. It is the ultimate resistance offered by the material. Though there is a decrement in stress, but at point D it gains some strength. That rod under testing, that material under testing gets some strength at point D, and hence there is increment in stress with increment in strain. Corresponding stress, corresponding strain, corresponding stress and corresponding strain. That is, there is increment in stress as well as strain. Look at this. This is the value of strain at this point and this is the value of stress at this point. At this point the material gains strength and there is increment in stress. Stress, strain, stress value, strain value, and this is the maximum value of stress. This is the corresponding value of strain. Now this is the ultimate stress, maximum resistance offered by the material to its breaking. That is the ultimate stress, and this is the actually a design criteria for the ductile materials. Ultimate value, ultimate stress, sorry, brittle materials. This is the design criteria for the brittle materials. Ultimate value, it breaks at sigma ut, that is ultimate, and sigma yt is the yielding, because yielding occurs in ductile materials, but without any yielding in case of brittle material, the material breaks at ultimate value of stress. Now if you look this between A and D, the stress goes on increasing till the point E is reached. From point A, if we observe, there is increment in the value of stress up to point E. The gradual increase in strain of the specimen is followed with the uniform reduction of its cross-sectional area. We know that if we just pulling the component or rod, that is means when we are applying a tensile load, there is a decrement in, that is the increase in length and decrement in the cross-sectional area of the component. As cross-sectional area of the component will go on decreasing, the value of stress also goes on decreasing, because the stress is equal to applied load upon cross-sectional area. As we are applying load, there is an increase in length but there is a decrease in area. So value of stress also goes on decreasing as we are applying the load on the component. Now the work done during stretching the specimen is transformed largely into heat and the specimen becomes hot. At E, the stress which attains the maximum value is known as the ultimate stress. It is defined as the largest stress obtained, have a concentration. Point E is known as the ultimate stress and it is defined as the largest stress obtained by dividing the largest value of the load reached in the test to the original cross-section area of the test space. Original cross-section of the test space. Keep in mind, it is the value of largest load applied in a test to the original cross-section area of the specimen. Now from point E, there is a slight decrement in stress, though there is an increment in strain. Because it is the largest value of load in a specimen, test specimen. It is the largest value of load in a test. From this point onwards, the load goes on decreasing. Hence, there is a stress also goes on decreasing, but strain goes on increasing. After the specimen has reached the ultimate stress, a neck is formed. Neck means a neck formation will take place at the breaking point, which decreases the cross-section area. We know that when we are pulling a mild steel rod by applying a load, tensile load, at some stage, when it comes to break, there is a formation of neck. And at neck formation, the cross-sectional area will be minimum cross-sectional area. A little consideration will show that the stress necessary to break away the specimen is less than the maximum stress. Though the specimen has not broken here, the specimen will break here. That's why it is known as the breaking stress. Because from this point, the cross-sectional area will goes on decreasing, and if we apply a little load on a component, the component will break. Now from point E onwards, at any point the component can break at a small load, because at point A is the E is the ultimate stress, and at point E, if we look at the specimen, it will have a minimum cross-sectional area. And from point E, if we goes on increasing the load on the component, as there is a small cross-sectional area, for a little application of a load beyond point E, the material will break. That's why the breaking stress value will be lower than the ultimate stress value. It is this, again try to understand, the ultimate stress is the stress which we get by the application of maximum load in a test by original cross-section area. But breaking stress is the load divided by cross-sectional area, minimum cross-sectional area. Hence the material will break at a stress which is less than the ultimate stress. The stress is therefore reduced until the specimen breaks away at point F. The stress corresponding to point F is known as the breaking stress. So these are the some silent points on a stress-strain diagram. Have a look once again. The stress strain diagram, this stress strain diagram is drawn for a ductile material, that is the mild steel material. The stress strain diagram is drawn by taking the values of stress on y-axis and values of strain on x-axis. The stress we get by dividing the load value by the cross-sectional area of the specimen. And this stress strain diagram is drawn. This stress strain diagram is drawn by taking the load, by applying load and by measuring the corresponding elongation. By measuring load and corresponding cross-sectional area, we can determine the stress. By measuring the change in length and original length, that is the gauge length, we get the strain values. And when we get the stress and strain values, the corresponding curve has been drawn, and the nature of curve is like this for a ductile material in a tensile test. And there are total 5 silent points on this diagram. Point number 1A is known as the proportional limit point, OA. Within proportional limit, the stress is directly proportional to strain. Point B is known as the elastic limit point, means up to point B, means from O to B, the material will be in a elastic limit. That is the elastic limit point. Point number C is known as the upper yield point, means up to point B, the material will be in elastic stage. Beyond point B, the material will enter into the plastic stage. The yielding takes place at point C. That's why it is known as the upper yield point, and D is known as the lower yield point. Though at point D, there is a decrement in stress, but from point D, the material will again gain some strength, and hence it will offer more resistance to the breaking. Hence there is increment in the values of stress up to point E. Now point E is the maximum stress that has been reached in a tensile test, which is calculated by maximum load applied in a tensile test divided by original cross-section area, not the corresponding cross-section area, original cross-section area of the component. And from point E, now at point E, that rod will have the minimum cross-sectional area. Hence beyond point E, if we apply a little load, there is a chances of breaking a component. And at point F, the material will break. That's why it is known as the breaking stress. For designing of a component, if the material is of ductile, then we are using yield stress as a designing criteria, and if the material is brittle, then we are using ultimate stress as a design criteria. So this is the stress strain diagram, which will give the values of stress and strain of a material, breaking stress of a material, ultimate stress of a material, which are required for the designing of any component. So this is regarding the stress strain diagram, which is drawn for a ductile material. I hope you have understood the stress strain diagram. Once again, note that the stress strain diagram is drawn by conducting a simple tensile test and noting down the values of load and corresponding change in length. Thank you.